Okay, so I didn't never finish that last question number 27, because we don't do this kind of stuff. We don't multiply binomials. We never did that this year. I just kind of started doing the question, got halfway through before I realized this is not something we've learned to do, and it's not part of our program studies anymore. Also, going back to question number 22, same thing. That's basically we're factoring polynomials. That's not what so don't bother wasting your time trying to figure those ones out. Okay, so just scratch 22 and 27. I'll make an announcement in the classroom regarding that as well. Okay, so next question. Let's make it a little bigger. Which of the following scatter plots best shows that at a constant speed, automobiles with smaller engines are more likely to have better fuel economy? Okay, so this is like reading like a linear graph. These scatter plots just take points of data and they help to show a trend. So you can just kind of think of this as this is showing us like a line that looks like that. This is showing us a line that looks like that. This is showing us a line that looks like that, and this is representing a line that looks like that. So this is just a matter of trying to read and understand what a graph is saying. So again, it says which shows that at a constant speed, automobiles with smaller engines are more likely to have better fuel economy. So this constant speed part is just referring to a chart. Okay, we've got engine size, and we've got on the bottom, and on the side we've got the rate of fuel consumption, meaning how fast fuel is consumed. Okay, so if it's high on here, that means fuel is being consumed a lot very quickly. Okay, if it's lower down, fuel is being consumed very little fuel. And here, this is our engine size is getting bigger as we go this way. All right, so this would be like a small engine here, and this would be a big engine here. This would be lots of gas being used quickly, and this would be a little bit of gas being used. Right? Okay, so this one, and so don't worry about the constant speed part. It's just telling us that it has to be that everything is running at the same speed. It's kind of like as extra information in this one. Okay, what's important is we're comparing the engine size to how much fuel it uses. Okay, fuel economy is saying how good a car is at not at saving fuel. Okay, and so it's saying which of this graph best shows that small engines have better fuel economy, meaning that they use less fuel. Okay, they use less fuel. So if we look on our graph, the left side represents smaller, and as it goes forward, that represents higher, okay, engines. Bigger. I said bigger engines. So when the engine is small, if we were looking for a graph that proves when the engine is small, it uses less fuel, this one doesn't seem to add up because here's a small engine and it's showing that it uses a lot of fuel. So that's not right. B shows that here if we have a small engine, because engine size in liters, so the engine size is getting bigger, a large engine. This is showing that no matter the size, we're consuming about the same. So it's not saying that small engines consume a low amount of fuel. It's just kind of in the middle, and it doesn't seem to matter too much on the size. So it's not going to be that one. Here we have small engine, big engine, and here we have small engine. And look, this lines up with our line here, right? Here's our line. These 2 points line up here. We read over here, yeah, we're saying a small engine uses a little bit of gas. Medium engine uses more. A big one uses even more, right? We're reading on here. So this one seems to support that a small engine uses less gas. Now, here we have a small engine, using a little bit of gas. But as it gets bigger, it uses more gas. But then as it gets even bigger, it uses less gas again. So this is not really like a linear equation. We're looking for something that um, would show the gas at a constant speed. Because maybe, I don't know, there's something going on here. If an engine's getting bigger and it's using less fuel, that doesn't make much sense unless it's changing speed or something. Okay, so this would be our correct answer. Okay, so we're just reading graphs, reading linear graphs to get information from them. All right, we did this question in class. A spinner and a six-sided cube are shown below. What is the probability of spinning the color red and then rolling a 1 or 2? So remember, when we say and, we're multiplying. So spinning the color red, what's our probability? Well, we have 4 choices here, and red is only one of those. So we have 1 out of 4 choices. And then what about rolling a 1 or a 2? So that word or is important. If we could roll a 1 or a 2, we've got 1, 2, 3, 4, 5, 6 that we could roll on a dice. And it could be 1 or 2. So we have 2 choices out of a total of 6. If we roll either of those, we're okay. So we have 2 out of 6 choices. That'll give me my probability. So the probability of both of those things happening, we have to multiply those together. So I could simplify my fraction here, but maybe I'm just going to just multiply first. But you could also write that as, right, 1/3, 1 out of 3 if you want to. So sure, why don't we simplify that fraction? So we're going to multiply 1/4 times 1/3. 1 times 1 is 1. 4 times 3 is 12. So we have a 1 in 12 chance of rolling a color red and rolling a dice that's 1 or 2. Okay, next question. So this one says the temperature of a solution was taken or measured over a 60-minute period, over a 60-minute amount of time. The results were graphed on a scatter plot. Okay, so which of the following scatter plots show the line of best fit? So line of best fit meaning the line that best represents the following. That temperatures of the solution, which which of the following best shows the line of best fit for the temperatures of the solution over the 60-minute period? Based on what? On what it said here. So the temperature of solution was taken over a 60-minute period. The results were graphed. Okay. Sounds more like a science question. So we have time over 60 minutes and our temperature. What do they say about what's happening? They're just telling us the temperature over time. Okay. Line of best fit scatter plots. This sounds old too. We didn't talk about scatter plots. Well, hey, just for your fun and your information. So it has nothing to do. They didn't tell us the context of this question, but a line of best fit is saying, like, if we can measure some stuff, and it's kind of in real life, things aren't always exact straight line. Okay, a line of best fit is one that kind of averages out, right? It's going to be sort of in the middle of all our lines. That's what they call a line of best fit. I'm going to say you don't need to know this for the test. I'll confirm that, but this was not in our program of studies from this year. So here we can see this one. Does this line on C, does that fit that very well? Not really. It's kind of below the line. It's not really through them. So definitely not that one. D is also no good. The line they've drawn, all the data that we collected, these dots below it, that's no good. And A and B look very close though. So we would kind of want to see which one is, we'd almost have to count the dots that are above and below. One here, one there, three there, one, two. To me, the one that looks like the best fit is this one here, B. But yeah, we're just going to skip this question as well. Okay, I will confirm that again for you, but we should not need to know this. Okay, moving on here. It says we have a half pipe, such as those used by skateboarders is shown below. So here is our half pipe where skateboarders skate. And what are they asking us about it? They ask, what is the area of the curved surface of the half pipe to the nearest meter? Okay, so we're talking about this colored in part, the dark shaded part here, right? Talking about all of that. So they told us our diameter, and we know, and then they've told us the length here of this half pipe. Okay. So we want to know what the area, surface area of that part is. Imagine we were painting it. We wanted to know the surface area that we're covering. So with something like, say, think of a cylinder, and we've got, remember when we did surface area, we had to calculate the surface area of this circle and the surface area of this circle. And then we had to calculate the area of the part that goes around the cylinder, right? To get that, we would take the diameter of our circle and then we multiply that by the length, and that would give us the full surface area all around this outside part, right? So we would have, remember when we did a circle, right, times 2 for a cylinder, and then we had this part, which was equal to our diameter, which would be our diameter, so our circumference, which is pi times d, pi times our diameter, times the height or the length of this object here, right? Because we take our circumference and then we multiply that by the length. Okay, but in this case, we only want half of that. So we're going to do that, but then we're also going to multiply by 1/2 because we're not talking about all the way around a cylinder. We're talking about just half of it, right? So we would take pi times our diameter of 10 times the height is 20. And we're going to take half of that because we only have a half pipe. We don't have a full cylinder, right? If we did, then we would have all this area up here too. Okay, so let's punch that into our calculator. And I don't know if I have pi in here. I'm just going to use 3.14. So times 10 times 20 divided by 2. And I get 314 meters squared. And there we have it. Okay, moving on. So that was a surface area. That was a surface area question. Sorry about that. Technical difficulties. Okay, next one. Question 34. Which of the following expression, use the following expression to answer question 34. Which of the following powers is equivalent to the expression above? So we had questions like this on the Part A PAT, I'm not sure if they'll repeat those type again, but let's just do this question anyway. So we learned this rule that we have when we've got powers inside brackets and we have an exponent outside, we can multiply that exponent here and here. So for example, remember we learned something like this. If I have 2 times 3 to the power of 2, I can write that, I can multiply, I can put that exponent to each of these two numbers. So I can have 2 squared times 3 squared, right? We can represent it like that. We can write it like that. So if I have something though, like if I've got exponent inside here, that would be like saying I have 2 squared, and I have 3 squared, squared. So from that point here, we would have to multiply because we're doing an exponent to an exponent. So we would get 2 to the 4 times 3 to the 4 if we had those exponents inside. Okay, quick example. So now let's look at what we have. So on the top, I've got 2 to the 3 times 2 to the 4. All of that is squared over 2 to the 2 times 4 to the 3. Okay. All right, so let's see. We've got here 2 cubed. We're going to multiply that, so we get 2 to the 6. Here we have 2 to the 4, and we're going to multiply that exponent because we're multiplying an exponent to an exponent. So we multiply those. 2 to the 8. And on the top here, we're going to be able to add those afterwards, right? We have these two multiplied, 2 to the 6 times 2 to the 8. So we can add 6 plus 8. We're going to get 2 to the 14. And on the bottom, we had, now let's see, our answers here are either going to be 2 to the something or 4 to the something. So they're throwing a little trick at us. We've got 2 to the 2 squared times 4 cubed. I want to try to get this all looking like 2. I want to get that 4 out of there. So how could we express 4 cubed? What is 4 times? What number do we have to multiply together to get 4? Right, so 4 is a perfect square. So think about if we could write 4 as 2 times 2, right? So that's 4 cubed. We write 2 times 2 cubed. So that's the same as writing, we have that cubed and that cubed, right? Same as we did before. So that would be the same as saying 2 cubed times 2 cubed. Okay, so I'm just talking about this part here. So 2 cubed times 2 cubed. Now if we use our other power rule, we add these exponents together and we get 2 to the 6. So I'm going to replace, let me scroll this up. I'm going to replace this 4 cubed with a 2 to the power of 6. Okay, so let's just rewrite this part here below. So I have 2 squared times 4 cubed, but we just figured out we can rewrite that as 2 to the power of 6. Now if I add those two exponents together, 2 squared and 2 to the 6, we add those, we get 2 to the 8. Now I've got this here. I can subtract. I've got 2 to the 14 over 2 to the 8. So I'm going to subtract those exponents. 14 minus 8. I should get 2 to the power of 6. 14 minus 8 will be 6. So we went from here to here. So there we have it. A is my answer, 2 to the power of 6. That was a tricky one. We haven't seen a question like that where we had to take this and then figure this part out. Okay, but if we're going to get an answer using these power rules, we know we have to get these all to the same number. So I got them all to the same base of 2, and we had to do that by thinking kind of in reverse. That was a tricky one. Okay, definitely.